In this video, we are going to look at the law of cosines. But before we do, we should spend a little bit of time reviewing the kind of triangles we've been working with before in previous videos. For example, right triangles can use Pythagorean theorem when you have two sides and you want to find the missing third side, or trigonometric relationships like sine, cosine, and tangent, or their reciprocal functions if you are having some kind of combination of angles and sides. So what we're going to do here, though, is finish the non-right triangles. Now, when we have non-right triangles, we had some different letter combinations that dealt with angles and sides. For example, the law of sines was very useful when we had the following combinations: two angles and a side, where the side was not between the two angles, or an angle, a side, and then an angle where the side was between the two angles. These were easy cases. Where things got a little difficult is when we had the side-side angle situation, where one angle was across from one of the given sides, and that sometimes had either an ambiguous case where there were two possibilities, or there was one solution, or there was no solution. But there are other combinations that we can solve with different trigonometric formulas. For example, the law of cosines, which I might abbreviate as LOC in this video, the law of cosines will be used for these three-letter combinations: side, angle, side. Now, the reason why side, angle, side is useful for law of cosines is because the whole formula is based on that premise of only having just one missing piece of our third component, which you will see in the formula. We can't use the law of sines for this triangle that's pictured here because we do not know the side across from the angle. So the sine of A divided by A would have a missing piece, and then the sine of B divided by 3 would also have a missing piece, and with two unknowns, it's not going to work with just one law of sines equation. Now, another combination that would work for the law of cosines is side, side, side. And you're going to see two examples of each of these today. The formula itself is pretty much based on the Pythagorean theorem. Let's start off with that. A squared plus B squared equals C squared. Now, this is true for a right triangle. But what if the triangle's not a right triangle? Well, we would start off with C squared. This is the symmetric property. We're just going to write the C squared first, and then after the C squared, we're going to write A squared plus B squared. The reason why I like to do that is because then I can see this pattern. If I subtract 2AB and then multiply by cosine C, and capital C stands for the angle, we now have one of our three possibilities for the law of cosines. In fact, if we start with another letter that isn't side length C, if we start with side length B, now we can use the other two letters, A squared plus C squared, and just right there in itself, you'd see the Pythagorean theorem. But afterwards, we subtract 2AC. Notice in the formula, these two letters will match the two letters of the other two sides, times cosine big letter B. And you can see that the front and the end of this problem has the same letter. In fact, if we use the commutative property and switched the CA around, we would have a palindrome, BAC CAB. But most books don't do it that way. They choose alphabetical order, and that would make sense. So I'd like you to pause the video and see if you can finish this formula based on the previous two. Even if you could think of it in your head or write it down, the formula starts with A squared and then ends with the A at the end, with the B squared plus C squared in the middle, minus your 2BC times cosine of capital letter A. Now, I won't be writing these multiplication symbols. Usually when I make my formula, I'll try to put a little space in there. Or, sometimes I will. I'm going to be inconsistent when putting these little multiplying signs in there. But it is very important to follow your order of operation when doing problems like these. So for this first of 4 examples, we're going to first identify what kind of triangle it is based on its angle and side measurements. And you can see that it has 2 sides and an angle. And unlike the side-side angle situation that we had in the previous section with the law of sines, the angle is between the 2 sides. So this is a side angle side, which is going to be for the law of cosines. Later on in the unit, there will be a section where you will be given just any old kind of triangle, and you'll have to figure out which method to use. So let's use the law of cosines, and let's see what I'm trying to find. I'm trying to find missing side A. So I'm going to start off with my formula with a squared. And just because we are new to this, I'm going to write my law of cosines out like so, and plug in what I know. Well, I don't know my missing side, but I do literally know everything else. B squared is the side, B squared is the side 3. C squared is the side 4 minus 2, 3 times 4, times the cosine of 30 degrees. Please make sure your calculator is in degree mode. If it is in radian mode, then you would be telling the calculator you need 30 radians, and each radian is about 57 degrees, so that's not what you're needing here. Alright, so let's do some algebraic simplification. Here we have 9 plus 16, which is 25. Here we have 2 times 3 times 4, which is 24, and here I have cosine 30. Now I want you to think to yourself, what would you do next? This is a critically important step. There's a common mistake that's made when people sometimes see the 2 whole numbers here, and they say to themselves like, well, shoot, that's awesome. This is 25 minus 24, so that would be 1. And that would be incorrect. Because if you remember, the 24 is being multiplied by the cosine of 30, so this is actually something that has to go first, and then this will go second. So you can't actually take your subtraction out of order. I know you've dealt with much more challenging algebraic problems to get to trigonometry, but this is a very common mistake where people think that a squared is equal to cosine of 30, and it just isn't. So if you type this into the calculator, you will get a squared is equal to a decimal approximation of 4.215, and so on and so forth. I kept that decimal in my calculator and then took the square root, and my a value is equal to 2.05 units. Now I don't have to worry about the negative situation when we have a square root. We usually have to consider plus or minus, but thanks to being in geometry, we don't have to worry about that. So a is equal to 2.05. Now lucky here, we can actually, what's lucky about this is we can actually use the hinge theorem when we're done with finding our last 2 missing angles. We can then see if the small side is across from the smallest angle, medium across from medium, and large across from large. Now for finding the next one, we have to be very careful not to fall into the law of sines. Here's where something can happen. You get to this stage and you go, okay, great, now I've got 30 degrees in A, so maybe I'll use the law of sines because it was so much faster to find the missing angle. Be aware what you're doing, because if you pick the 30 degrees and the side A, and then you pick B and the 3, you've just picked a side-side angle. And you have a good chance, maybe better than 50% chance of getting the answer wrong, because I can tell you what, this answer is so small, there is the possibility that you will have picked a problem that has 2 possible answers, and your first choice may not be the correct answer. So heed this warning. Do not use the law of sines after starting with the law of cosines. Stay with the law of cosines. It won't steer you wrong. There is no ambiguous case for the law of cosines with a side angle side or a side side side. Although you might be wondering to yourself, how am I going to find one of these missing angles here? And I'm going to find the missing angle, let's see, which one should I find? I'm going to find the missing angle B from here, and that means I have to start with my side B. Since I have to find my angle B, I'm going to start with the side that the angle belongs to. And you're going to see that we can actually finish this problem using just that information. So, the B side length is known. And the A side length is also known because we just found it. And the C side length was given in the original problem. Everything else gets plugged in without getting squared here. And the cosine B is literally what we don't know. We don't know this angle B. So now we get to just kind of work with all the algebra that we have. If I combine these together, this will make 20.2. And if I combine these together, this makes 16.4 times cosine B. I said I was going to be a little inconsistent with this multiplication sign, but now that I've shown you the problem in that when we solved for side length A, you can see that I better put it there so I don't accidentally subtract these two and then try to divide that on both sides. What I need to do is I need to get rid of the 20.2 and the 16.4 negatively. So I'm going to subtract the 20.2. If I subtract that from both sides, this simplifies to 0. And this makes negative 11.2 on the left-hand side. Now everything else drops down like a Tetris piece, negative 16.4 times cosine B. Now I get to divide everything by negative 16.4. Negative 16.4. Okay, now these simplify to 1, and negative 11.2 divided by negative 16.4 is roughly 68 hundredths, and that's equal to cosine B. Now you'll note that this value is very important. It's important because it's a decimal, and it pretty much can't be a big number because it would break the domain restrictions of cosine, or I'm cosine in this situation, because cosine can't be greater than 1 thanks to the inverse rules. So if you ever get a number that's bigger than 1 or a number that's negative here, you've made a mistake. Please go back and check your algebra. So what I'm going to do is take the inverse cosine of both sides. So in my calculator, if I type in the inverse cosine of 0.68, because that's taking the inverse cosine of both sides, this will give me the decimal of 46.93, and this just gives me B, and B is what we're trying to find, which is the angle, 46.93. And this is a rounded number. Sometimes you'll get a slightly different decimal depending on how you rounded it, and the book rounds it to the nearest tenth, so the book rounds it one step closer to the whole number than I do. Now, if you're feeling like, well, how are we going to find the last missing angle? Well, that's the best part. Finding the last missing angle is subtracting these two from 180 degrees. So 180 minus 30 minus 46.93 is 103.37 degrees. And again, look in the book to see how you did. You might find that, oh, looks like I was off by a little bit here and there. But what's cool about this is that if you're close enough and you show your work, you're going to be fine. And that was the end of my first of 4 examples for the side angle side, or the law of cosines. Let's see which one we get next. For this next triangle, and some of you might notice that I'm not doing all the examples that I might have handed you in the work packet. It's because some of them are actually a homework assignment, so I'm not going to do every problem that's maybe on the home or the notes packet, but let's do this problem. I'll label this problem 12 here. This problem is another side angle side triangle, because here we have a side, here we have a side, and here we have an angle, and since no angle is directly across from a known side, we can't use law of sines. We have to use law of cosines. So what's the side we're trying to find? Well, that would be the side B. So b squared is equal to a squared plus c squared minus 2ac cosine capital letter B for angle B. What's nice about the side angle side triangles is they give us all of the algebra on one side of the equation. So we know our a, which is 2. We know our c, which is 5. And we'll plug it in here as well. And now we get to do some algebra. So this is going to be 4 plus 25, which is 29, minus 2 times 10, which is 20, cosine B. Please resist the urge to say that 29 minus 20 cosine B is 9 cosine B. That is incorrect. That is not right because of order of operations. You have to multiply the 20 times the cosine B, cosine not B. We actually know the answer B. Silly me. We actually know that this is cosine of 20. All right. So we definitely need to multiply this first, then subtract it. Now, thanks to the fact that I did this on my calculator earlier, this is 10 and 21 hundredths. It's a much longer decimal, but I've rounded it to 2, and then I'm going to take the square root of it to find my side length B, which is 3.19 units. So here's my side length B, 3.19. Now what I'm going to do is I'm going to use that side length and this known angle, and I'm going to find, let's see, which one do I want to find? Let's find angle A first, okay? Let's find angle A. So here I'm going to need my equation that starts with an A. So a squared, not plus, I almost wrote the Pythagorean theorem there for a second. This is a squared equals b squared plus c squared minus 2bc cosine capital letter A. Now, in this situation, I know my side length A. That was given. I know my side length B because I figured it out, and I know my side length C because it was given. Minus 2 times 3.19 times 5. Cosine, I do not know angle A this time. So it's time for me to do a little bit of algebra and not run into my other example here. So I'm going to move a little bit to the left here. 4 is equal to 35.2, and the 35.2 was created by taking these two together and moving it over there. And then the minus 2 times 3.19 times 5 is going to be negative 31.9, and then the cosine A, which I don't know. Again, resist the urge to subtract these two. You in fact have to subtract the 35.2 on both sides, and that simplifies to 0, and this simplifies to negative 31.2, which is important because on the other side we have a negative 31.9 cosine A. And it's important because you have to divide both sides by two negatives, and getting a positive answer should make you feel good like you're doing the right thing, because you are. So these two simplify, and the 31.2 divided by the 31.9 is going to be approximately 978 thousandths, and that's equal to cosine A. Oops, let me clear that up a little bit here. Okay, back again. Trying to write cosine A. Okay, so we take the inverse cosine of both sides, and if I take the inverse cosine or type this into the calculator, and granted this decimal is a lot longer, but it is rounded, I'll get to an approximation of A, which is 12.04. Now, if you look at your answer in the book, you might notice that this is different than the book. This is a rounded answer because I've been making rounding adjustments all the way through here, but this gives me my angle 12.04. Now what I'm going to do is go up to the top here and subtract everything from 180 degrees. If I subtract everything from 180 degrees, then I get my final answer of 147.96 degrees, which is pretty good. All right, on to the next and our last two problems here. We just had two side angle side triangles, so it's probably time to bust out some side situations. For this third example, we are going to now see our first side-side-side triangle. This is the easiest to identify because you are given no angles. You can find any of the missing angles using the law of cosines. And we're going to start off, and students sometimes ask, well, which one should we start with? Well, why not A? I have found over my course of teaching this lesson that most students have the easiest time starting with A. I don't know if it's symbolic, perhaps there should be a psychological study done on it, but for the most part, just start off with the letter A, and then we'll find letter B, and then we'll use the property of 180 degrees to find letter C. So, starting off with the A squared, we know that that's 8, because that side length is always across from its angle. So, that's where each of these line up to. And my B is going to be, in this case, 5, and my C, in this case, is going to be 4. Minus 2, oh, that's a plus here, minus 2 times 5 times 4, cosine A, the missing thing we need to find. So this is going to be 64. 25 plus 16 is 41. Minus 2 times 20 is 40. Cosine A. Resist the urge to put these together and say that that's 1 cosine A. So you subtract the 41 from both sides, and that gives you an answer of 23. And that's equal to negative 40 cosine A. Divide both sides by negative 40. Are you getting a little nervous because one of these is negative and one of these is positive? Well, you should be a little nervous, but it's actually going to be okay. Thanks to possibly the obtuse angle, we should actually get a pretty good answer, because this is negative 0.575, and that's equal to the cosine of A. And what I haven't been doing is showing my step of taking both sides, taking the inverse cosine of both sides. So just want to maybe show you, I don't really have a lot of room to write it, but if I have the inverse cosine here, and I take the inverse cosine here, the inverse cosine of cosine A is just A, and the inverse cosine of negative 0.575 is an obtuse angle, 125.1 degrees, and thanks to the fact that we have a picture of this, we can actually see it right there, which is nice. Angle A is obtuse. Now let's find angle B. So it's really repeating this with the B squared is equal to A squared plus C squared minus 2AC cosine B. That looks a little nicer. So we're going to put in our sides, and you got to be careful about this to make sure that you're isolating B's side and then putting inside here A and C's side. Minus 2 times 8 times 4 cosine B. And again, this is what we don't know. So I got 25 is equal to, now 8 squared plus 4 squared, or 64 plus 16 is 80. Minus 2 times 8 times 4, which is 64 cosine B. Subtract 80 from both sides, because I cannot combine these two whole numbers. So I've got an answer here of negative 55 is equal to negative 64 cosine B. Divide both sides by negative 64. I get an answer of approximately 86 hundredths. The decimal's longer than that, but for the sake of me writing your notes down, I've just shortened up here. I take the inverse cosine of that long decimal, and I get a B value, which is my angle B, of 30, no decimal there, 0.8 degrees. So B is 30.8 degrees, which means my angle C, if I subtract 180 degrees minus 125.1 and 30.8, this gives me 24.2 degrees. And that is my third of 4 examples. For our final example in this law of cosines problem, we see another side-side-side example. It's side-side-side because these are the 3 sides given. What's nice about this is if you're a little clever, you can actually skip a pretty big step after the first part of this problem. Of course, the first part of this problem is figuring out angle A. So we're going to put a squared is equal to b squared plus c squared, just like the Pythagorean theorem. But unlike the Pythagorean theorem, minus 2bc cosine A, we now need to find the missing angle A from what we know. We do know that side A, which is across from angle A, that's 4. We do know B side length, which is across from angle B, is 3 squared. And then the last missing one would be this 4 squared right here. Minus 2, 3 times 4, cosine capital letter A. Okay, so let's do some algebra. 4 squared is 16. 9 plus 16 is 25. 2 times 3 times 4 is 24. Cosine A. Again, resist the urge to say 25 minus 24 is 1 cosine A, because this 24 cosine A, consider it like a term. Consider it like 3x. And we can't say that 25 minus 24x is 1x. So we have to treat the 25 like that, subtract, that simplifies, and this will give you an answer of negative 9, and that's equal to 24 negative cosine A. Make sure that gets brought down as well. I almost forgot that just right there. So we take the 24 and divide that on both sides, like so. And what you get there is some nice simplification. The negative 9 times negative 20 divided by negative 24 is positive 375 thousandths cosine A. Take the inverse cosine of both sides, and what you get is A is equal to a rounded decimal of 67 and 98 hundredths. So this is angle A, 67.98. Now, can you see a way to shorten your work on this problem? Normally, we would erase this work or continue writing in a very small fashion to try to find angle B. But do you know what kind of triangle this is? Oh yeah, I know. Side, 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 right? Well, actually, this is a triangle that has 2 equal sides. It's isosceles. And isosceles triangles not only have 2 equal sides, but thanks to an extension of the hinge theorem, they have 2 equal angles. If you tilt your head to the left, you can see that angle A and angle C are exactly the same. You can measure them, but we don't need measuring because the hinge theorem says that the sides correlate to the angles in the picture, and you can see that C is across from a 4, A is across from a 4, so C therefore must be the same angle measurement as A. Which also means we can now get to the end of the problem lickety-split, because we can now subtract these two from 180 degrees, which I've done and found that my angle B is 44 and 4 hundredths. And if I add all these three up, it adds up to 180 degrees. You might find again that the book has rounded a little differently, but as long as you're close, you're good. Well, thank you very much for watching this video on the law of cosines for the side angle side example and the side 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 example. Thanks for watching.